All right, so today I'm going to introduce to you the idea of electron configuration and ions. So last lesson we talked all about electron configuration, and you could take a look at the periodic table, you look at the back, you pick something such as carbon. We're going to look at carbon 12. It has 6 protons, atomic number 6. If it has a mass of 12, we would have 6 neutrons. Remember, mass, atomic mass, equals protons plus neutrons. If you don't remember that, you need to keep quizzing yourself every night. You should know this. I'm going to focus it. Awesome, focused. Okay, carbon 12. What is the full electronic configuration? Okay, well, what row is carbon in? It's the second row. That means it's going to have the N equals 2 shell. It's over in what's known as the P block, that section on the left where there's 6 columns. So it's going to have 1s2, as every element has, except hydrogen. 2s2, 2p. How many over is it in the thing? Take a look at that. P block. So this section is the P block. 1, 2. It's going to have 2p6. Awesome. Okay. Before we get too much further in, let's take a quick look. You can follow along and read about this on page 262 in this book. But let's take a look at what these columns are, about talking about the families in the periodic table. So, this first column, highly reactive elements, typically metals. These are the alkali metals, highly reactive. They have a single electron in their valence shell that they usually don't want. Next to them, the alkaline earth metals. These are reactive as well. They also have 2 electrons. They don't want those electrons. They're going to end up easily forming ions. The reactivity relates to how easily they may form an ion or a compound. So this is the S block. 2 columns, 2 electrons in S, one S1, S2. Alkali earth metals, alkaline earth metals. Then this 3D block, this D block, the transition metal. 10 electrons that go in the D block, 10 columns. These are things that will do sometimes strange things. I'm going to talk about 2 exceptions. I'm going to talk about chromium, and I'm going to talk about copper when you're doing electronic configurations next. Down here, we have what's known as the F block. You don't get access to the F block until you get all the way down here into row 6. Then in row 6, the electronic configuration, we'll go over this as well, is going to look something like xenon, 6x2, 4f14, then 5d, 6s. I'll do a few examples of those just so you can see them. Then over here we have what's known as the P block. P block can hold, the P subshell can hold 6 electrons. Of those 6 electrons, there's 6 spaces as you go across, filling each one. Just think, Mendeleev created this back in the 1800s when so little was known. He was able to organize it and predict what it would look like, and the spaces have since been filled in with a few changes. Within these, this line, boron, silicon, arsenic, tellurium, astatine, septium, and octium, these are aluminum, germanium, antimony, polonium, hexium. These are metalloids. They might behave like metals, they might behave like metalloids, depending on their company. Then here we have well-established nonmetals, typically gaseous. This here, column 17, fluorine, chlorine, bromine, iodine. These are halogens. They are also highly reactive. They're missing an electron to fill that p orbital. And that filled p orbital gives you a noble gas configuration. Noble gases are what every element, I realize you can't see this. Sorry. P block, metalloids, halogens, highly reactive. They want to have an electron configuration like this. We'll talk about these little numbers later. Electronegativity values, essentially how much they want an electron. 4 is the max. Fluorine really wants that electron. It's important to it. 0.7 over in francium, doesn't want it as much. All right, let's talk quickly about these exceptions of copper and chromium when filling electron configurations. Okay. Oops, this was back here. That was 2p2. My apologies. So chromium, let's write the core notation. The core notation, well, chromium is row 4. You're going to look back at this noble gas of row 3, that's argon. So it's going to be square bracket AR. Okay. You're going to go over, okay, chromium, it has a 4s2. And then it has a 3d 1, 2, 3, 4 over. All right. How many electrons can the d orbital have? Take a second and count. If you counted 10, you're correct. 4 is halfway to 10. So it's half filled. It really would like to have everything there. So what ends up happening is, instead of that, you get this configuration. It's kind of like a middle ground is reached. It takes an electron from the 4s orbital, making it 4s1. 3d5. Now it's half filled. It's more stable that way. It's happier that way to personify. So this is exceptions. The other exception is copper. The core notation of copper is again argon. It's all the way in the 9th one over in the 3d shell. So it has a 4s2 and a 3d9. Okay. 3d over is almost filled. It's so close. So what ends up happening is it takes that electron from the 4s and it fills the 3d. For whatever reasons, electronically speaking, it is more satisfied that way. So let's take a quick look at the lanthanide and actinide blocks. So let's do a lanthanide electron configuration. So I'm going to pick element number 65, terbium. Terbium. It's number 65. It has a mass of, I'm going to use 159. So it has 65 protons, which means it would have 65 electrons. And if I do 65 minus 159, (94 neutrons). I'm not going to ask you to draw the electron configuration diagram, the Bohr models. So if I wanted to go through and I wanted the full electron configuration, it's going to be long. Let's try that out. Focus this in. I don't want this messed up. Okay. Terbium, Te. 1s2. Okay, good. Got the first step. 2s2, 2p6. Oh my goodness, I already made a mistake. 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. So 5p6 takes us up to xenon. Well, if you look at your table, the lanthanides are taken from element 57 and kind of inserted there. So we need to look at that. The next is 6s2, 4 F, 4F. I haven't talked about that before, but lanthanides are F blocks. So count over how many is there? Well, key is counting lanthanide. 1, 2, 3, 4, 5, 6, 7, 8, 9. 4, F, 9. Crazy. Core notation. I said xenon. 6s2, 4, F, 9. Now, what does a transition element after that look like? Let's look at osmium. Osmium will go with a mass of 190. Osmium 190. It has 76 protons. (124 neutrons). I'm just going to start with the core notation of xenon. Six S2, 4 F. Again, go starting at lanthanum, counting over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 14 is that. Then we start the number 71 luteum is then one more. So that's the starts the 5D. So 4F14, 5D. 1, 2, 3, 4, 5, 6. 5D6. That's what that would look like. All right, that's all I'm going to talk about that. Again, going back to your textbooks, isoelectronic configurations to noble gases is what is being desired by most elements. I need a new piece of paper. Oh man, where's that note? There it is. Okay. So first I'm going to start with isoelectric. Isoelectronic. So this, in chemistry terms, is having the same electronic configuration as another element. And this is the driving force behind ionization, essentially. So when we ionize, we want to look at the valence electrons. Valence electrons are the electrons that can take part in a chemical reaction. The outermost electrons, which can take part in chemical reactions. Electrons in the core do not participate. In reactions. Or electrons in filled D or F subshells. Okay? So the valence electrons are what electrons you have after the core notation. Let's take a look at something like chlorine. Okay, chlorine. Number 17, mass of 35. Chlorine 35. Okay. This is a notation writing that's like this to demonstrate what you have and the mass. You don't always need to write the protons because those are not going to change. If those change, you've undergone a nuclear reaction and you've changed that at its core, at its whole. So, chlorine. The core is neon. It's in the third row. 3s2, 3p5. So, to get the number of valence electrons, how many electrons are in the outermost shell? So you can count these electrons in unfilled. So, 1, 2, 3, 4, 5, 6, 7. It has 7 valence electrons. Okay. Let's take a look at what's next to it, argon. Argon 40. Well, its core configuration is neon. These are contracted in. We haven't talked about size and contractions yet, but these don't react. It has 3s2, 3p6. So add your S, add your P. The outermost shells. Two plus 6. 8 valence electrons. Wait, okay. Let's take a look at potassium next. Potassium 39. What's its core configuration? Argon. Whoops, 4s1. Okay. 1 valence. Okay. Now these are 3 different types. Chlorine, where's chlorine? Chlorine is a halogen gas. Argon is a noble gas. And potassium is alkaline. Noble. I need to double check that spelling. Alak. Alkali. Right. These are 3 representations. Noble gases. Why are noble gases so stable? They're very unreactive. They're so stable because their valence electrons are filled. They have what's called a full octet. So think of octopus, octagon. That's all I got. Octet, 8. Octahedron, 8 sides. Octet. That's what other elements strive for. Neon, 3s2, 3p5. It's 1 valence electron away from having a full octet. Potassium, it has 1 more electron than a full octet. So essentially what ends up happening is, sorry, I gotta go check my kids. I'll be back. 9. All right, so picking up where I left off, we want things that are going to fulfill an octet. That's when they're happy, and this is how we form ions. So let's take a look at chlorine. Chlorine has 7 valence electrons. Let's write out again its configuration. Halogen gas. So it wants to fulfill what's known as the octet rule. And fulfill its octet. How many electrons? If it has currently 7 valence electrons, how many electrons does it need to fulfill an octet? It wants 1. It needs 1 to get to an octet. Does it have space in its orbitals for 1 more electron? Take a look. I know I'm running on paper. So you're looking, well, it has 3s2, 3p5. How many electrons can fit in the p orbital? How many? Are you sure? You're right, 6. So I have 5, and I can fit 6. Okay. If there's an available electron hanging about, do you think chlorine's going to be like, hey, come with me, and it's going to really want to take it? Okay. So the p orbital can hold up to 6 electrons. Awesome, great, wonderful. So what's going to happen is it's going to pick up an extra electron from somewhere. It's going to gain 1 electron. And where is it going to put that electron? It's going to put it in the p orbital. Okay. Do you think it's happy? I think it's happy. How many electrons? It has 8 valence electrons. It's happy. But it's not chlorine anymore. It identifies slightly differently. Now what does it identify as? Well, if I give you more electrons, you'd feel negative, minus charged. Cl minus. Chlorine minus. It's a chlorine ion. And if you go through and look at it, chlorine, atomic number 17. Chlorine has in its regular state, it would have 17 electrons, correct? 1 electron for every proton. If I made it into an ion, I've plus 1 electron. So that means I have 18 electrons. Okay. I have more negatives than I have positives. So I have 17 pluses, 18 minuses. Everything's going to cancel, but I'm going to have 1 minus left over. And that's going to give me a chlorine 1 minus, a negative 1 ion. Okay. If you look at everything around chlorine, fluorine, bromine, astatine, they all have 3p5. They're halogens. Trends in the periodic table will tell us that they're all going to want to gain a 1 electron, and they'll be happy. They'll be like, yay, I've made it. Let's take a look at something in the opposite side, like potassium. Potassium. This is page 3. Potassium. Okay. So potassium has an argon 4s1. Configuration. How many valence electrons does it have? 1. All right. So, how many does it want? It wants 8. With chlorine, it was nice because 7 is what it had, and it wanted 8. That's just easy. 1 more. Take that other step, gain an electron. Now we're faced with potassium, which only has 1 electron. It's like I could care less about this electron. I can just as easily get rid of it as chlorine could gain 1. So, for potassium, it is easier to remove an electron or lose an electron than to gain 7 electrons. What happens if it loses an electron? So for chlorine, we saw gaining an electron would make it have 1 more. It would become isoelectronic with argon. That's what I forgot to mention, isoelectronic. So it now has 8 electrons. It is isoelectronic with argon, the noble gas. That's what it wants, that configuration. So potassium, it would have to gain 7 electrons to be isoelectronic with its krypton. Is it feasible to gain 7 electrons? No, it's not. But it can lose an electron. It's going to be easier. Hey, get rid of removes / gets rid of. Atomic number 19, yes. All right. So, it can remove 1 electron. It starts with 19 protons. And 19 electrons. It removes 1. It takes 1 away. Removing, taking away. It now has 18 electrons. Well, if we go through, and cancel it out, we end up what we have is 19 positive, and 18 negatives. Cancel it out, we end up having a 1 positive left over. This is how you determine the charge. If it loses electrons, it becomes positive. If it gains electrons, it becomes negative. I'll write that out later. So, let's look at the 4s1. If we're removing that, we're going to take that away. K plus has, I remove the 4s1 electron, it now has argon's electron configuration. It's got the electron configuration of a noble gas because of the removal of a single electron. Okay, awesome. A potassium ion K plus is isoelectronic Cool. All right. There's some things. So let's take a look at beryllium. I don't know why I choose beryllium. I can never spell it. B-E-R-Y. I was gonna put an extra I in there. So beryllium. We'll go with beryllium 9. Has an atomic number of 4. Okay. So electronic configuration, second row. It has a core of helium and 2s2. Awesome, great, wonderful. Yay! So, it has 2 valence electrons. Something slamming inside, kids playing, who knows. It's a long ways away from 8. Similarly to potassium, it's more easily for it to lose 2 than to gain 6. So what ends up happening is it goes from beryllium with He2S2 to to 2 electrons that it's releasing. Its arrow going to go, it's going to release these. To beryllium 2 plus with a helium configuration. Whoa, cool, awesome, great. Let's do that again. So let's take a look at calcium. Write the core electronic configuration: calcium, argon, 4s2. Okay, argon 4s2. How many valence electrons? 2. Do you think it's going to lose or gain electrons? It's going to want to lose electrons. So we're going to go with calcium with an argon 4s2. It's going to lose 2 electrons. So it's going to separate itself from 2 electrons. And it's going to become calcium 2 plus. With an argon configuration. Sound okay? Take a look at fluorine. So, fluorine has a helium 2p5 configuration. Sorry, 2s2 2p5. So it has 7 electrons. It wants 8. It's going to pick up 1 electron. It's going to become fluorine minus, and it's going to have a helium. And then 2s2 2p6. Let's try oxygen. Well, oxygen has a helium core, 2s2, 2p4. So it has 4, 5, 6 valence electrons. How many does it need? 2. So it's going to add 2 electrons to itself. Oxygen becomes O2 minus with a helium, 2s2, 2p6 configuration. Those are a few examples. Homework. I want you to write the ionic electron configuration. Of the following. Just like I did it for beryllium, calcium, fluorine, oxygen. Just like that. Number 1, H minus. Number 2, Na plus. Number 3, Sr2 plus. Number 4, titanium 2 plus. No, titanium 4 plus. Number 5, that one's going to be a little tricky. Number 6, N2 minus. N3 plus. Tellurium 2 minus. Iodine minus. Cesium plus. Manganese 2 plus. So, a summary of the assignment. Summary. Number 1, electrons in the outermost shell are removed first. That's the largest N. 2, If there are electrons in both s and p orbitals, of the outermost shell, p orbital are removed first. So when you're adding electrons, you're just adding them to whichever shell is available. So in summary, you can say remove electrons in this order. P before S, before D. P electrons first, S electrons second, D electrons last. Adding electrons doesn't matter. You're not always able to be isoelectronic with a noble gas. You're not always going to get the same configuration as a noble gas. So I want you to work on that in the next few days. I'm going to try to come back earlier next week, maybe Tuesday, get something out to you. That's going to take quite a bit of mine. So, good luck. Have fun. Enjoy the weekend. Work on the chemistry. Work on back stuff. If you're missing work that you know you haven't done and it's not filled out for a mark, and I'm going to go through and do back marking this weekend, get work on that. It's your responsibility to get yourself passed. I can let you know. Everything's on the website. Have a great day. Have a great weekend. Bye.